working at a health tech company in California. My training as an undergraduate was in computer science, and I concentrated in artificial intelligence. I am pausing my graduate studies, but hoping to continue in biomedical informatics. So today I'm going to talk a little bit about three terms that some of you may have heard of, or none of you may have heard of. They're artificial intelligence, machine learning, and deep learning. And I think that today, largely as a function of the media, but due to a lot of other reasons as well, when we think of artificial intelligence, most of the images that come up and enter into our minds looks like this. And as a data scientist and as a practitioner of AI, I would like to push forward that most of the time we look at things that look like this. And although it's not necessarily as sexy or as seemingly scary or foreign as the image of a robot or the idea of the singularity per Terminator or the idea of superintelligence, general intelligent AI that surpasses the human capacity to think in every way imaginable, it's actually a more narrow version of AI that's applied to more narrow problems, specific and well-defined problems, that defines the field of data science today, and that actually is becoming more and more ubiquitous throughout our daily lives. There are an increasing number of AI models being deployed every day by researchers, by students, by companies, small and large, that affect hundreds of millions of people like you and myself. And to me, that and this picture makes those ideas equally, if not more compelling than that of Will Smith and the iRobot. So let's not get ahead of ourselves. My main goal for today is to demystify those three terms and to hopefully make it so that we understand that AI is becoming more ubiquitous. We understand that, and we also understand that it's getting harder and harder to see. It's not the robots, it's not the superintelligence, it's algorithms that tell us how to get from place A to B through Google Maps. It's algorithms that make it so that when I Google Stanford, and I'm sitting right beside you, and you Google Stanford, the search results might look nothing alike. So at the end of this talk, and hopefully with a few questions, I'm hoping that that idea will really stick, that even though the products you use are probably the same now as they were 2 or 3 years ago, the workings behind them are probably a lot different. So how many of you in the audience today have ever used Google Translate? Okay, not a very long time ago, Google Translate was a very bad product. The translations were not usable in any way, shape, or form. What I'm about to show you on the screen is an example of a Google translation of an Ernest Hemingway book. The book was written in English, translated into Japanese by a human translator, and then back into English by a machine, just for testing purposes, shall we say. This is what the machine came up with. Pretty bad translation. I don't think you could infer from this paragraph what was going on, what it was trying to explain, and certainly all of the literary merit has been lost. So keep this paragraph in mind for a second and how you feel about the performance of this model. Going back to the definitions, I think that artificial intelligence, or at least how it's being used a lot today, is a misnomer. The ideas have been around for a very long time. They've been around since the 50s, and a lot of the concepts were used in World War II. If any of you have seen The Imitation Game, Alan Turing and his work and the work of his predecessors were all considered artificial intelligence and contributed to this deluge of terms and deluge of techniques that we're experiencing today. A subset of those techniques is called machine learning. So like I said earlier, artificial intelligence encompasses search, it encompasses game playing. So if you, friends, children, parents, have ever computer games, whenever you're playing against a computer, they're using some notions of AI. But there are a lot of other aspects that these very general models can also be applied to, a lot of other problems. Machine learning, even though it's only appeared, I think, a lot more in the news in recent years, has also been around for a very long time. And a lot of the techniques that I use at my work and a lot of the techniques that researchers at Stanford use and have subsequently taught to their classes have been around since the 70s and 80s and have remained largely unchanged. In fact, most of what's changed is not the mathematical techniques, but it's in the amount of data that we've been able to collect, it's in the amount of data that we've been able to clean and process, and it's in the computational power that has come through companies like NVIDIA, Google, Amazon, and in democratizing access to simple algorithms and allowing them to be used at scale a lot faster than they were able to be used in the 1950s through the 1980s. Fast forward to 2010, I don't know if any of you have heard of the term deep learning or if you've used it in your work or if it's being used in your offices. But deep learning is another subset of machine learning that is able to sift through vast amounts of data, like the language data that went into Google Translate, the language data that was used to train previous models, photographic data that you put on Facebook, photographic data that exists on Google Images and Flickr, Creative Commons, Wikipedia, whatever. All of that information on the internet is fair game for these models, and deep learning has come up as the de facto best performing model as of late and most appearing in research as of late because it's specifically suited to having large amounts of data and to use the technologies that have only come up in the last few years in terms of being able to process those large amounts of data. But again, the techniques that are being used for deep learning today have been around for a very long time. If you Google a lot of the research papers that have deep learning in the title, you'll see citations from the 70s or even the 60s in some cases. But one thing that makes machine learning and deep learning unique, or one of the main thrusts of why they're so significant today, and how they've been able to improve models as they have been able to, is because previous to machine learning and the advent of these techniques, when you wanted to tell a computer to understand something, you would have to explicitly encode what you meant. So, for example, if I wanted a computer to understand language, I would have to teach it somehow what a noun was, what an adjective was, how they related to each other, parts of speech, what a phrase was, what an incomplete sentence was. And as you can imagine, the list becomes very long and very cumbersome and results in a lot of lines of code. And that's how we had this very bad model over here. But now, with machine learning and deep learning, all of that goes to the wayside. It recognizes patterns in the data, and through some number crunching and through some feature massaging, which I'll talk about later, it's able to recognize these patterns, learn when it's wrong and right, and infer and make predictions about what you give it, and answer questions about what you want to know. So this was an old Google Translate model, and after introducing deep learning techniques to the Google Translate team, I'm going to show you the next slide that has two translations. Same deal. Ernest Hemingway book, translated into Japanese by a human, translated back. One of these paragraphs was translated by, and one of them by a deep learning model. I'll give you a few moments to read it, and then I'm going to ask you to decide which one you think is which. Who thinks that the first one was written by a machine? Who thinks that the second one was written by a machine? All right. It's a lot harder than the first example, huh? I'll give it away. The second one was written by a machine. But for most people, it's only the absence of an article over here that gives it away. four-letter. But by most accounts, this is a functioning translation. I would be much more satisfied going to a foreign country with a language that I didn't speak using this version of Google Translate versus this one. So deep learning has enjoyed a lot of great successes in recent years for well-defined problems like the Translate one, with a lot of data being fed into the model such that it can make predictions and inferences like this one. Now, one of the things that I deal with on a regular basis at work and in my studies and talking to other researchers is how do we make paragraphs like this one, words like this, humanly intuitive concepts into machine understandable ones? Because paragraphs like this, words by themselves are not immediately understandable to a computer. So one of the ways in which we do that is, let's say we have the word cat. Cats are often used in machine learning research. If you Google any of the research nowadays, you'll find a lot of things about cats. We want to make this word cat understandable to a computer, because right now it really isn't. Well, one way in which we can do that, and an active area of research, is in creating embeddings. And embeddings are just a list of numbers, say for cat, some random numbers, that we're going to use to represent the word cat in a way that a machine can understand. Now, one way to think about this is, let's say I'm a person, this is me, and I want a list of numbers to represent myself. We do this all the time, and we've done it before the advent of machine learning. Let's say I'm age 22, I'm about 163 centimeters tall, I'm about 110 pounds, and I can create a longer and longer list of things that I think describe me. And this list of things, in terms of numerical values, is in fact understandable to a computer. So going back to our example of the word cat, if we want a computer to be able to understand the concept, I'm going to get into a little bit of math and a little bit of graphs, but I promise it's only for a short time. Say there are three axes, right? Three numbers, three axes. Usually it's a lot more, but longer doesn't always mean better in terms of the number of features that you have. Using these three numbers, I can find the 0.3 on the x-axis, the 0.5 on the y, and the 0.1 on the z. Let's say cat goes somewhere here. When I say that I want these concepts to be not only machine readable, but also machine understandable, I want to make sure that where they are in this space makes sense. We know that cats have most likely have fur, they most likely have pointy ears, they most likely have four legs. We want all of those concepts, whether they consist of one word or more words, to be close to this idea of cat. We also want the notion of a dog to be close to the idea of cat. We also want more nuanced explanations or concepts related to that of a cat to be close to the word cat in this three-dimensional space. Let's say meme. If any of you have seen memes online, a lot of them are related to cats. So you would also want the word for meme to be pretty close to the word for cat. So how do machines learn this? Well, one way in which it does it, and I've hidden the math from some of this, is through a model. This particular one is called a language. It's a language model whose name is cumbersome, and we can Google it later. But effectively, it takes in a number of sequences of words, sentences, and documents. And it learns which words are used next to each other in the same context such that the sentences make sense. So by feeding in a bunch of sentences into it, let's say the corpus of Wikipedia, this machine learning model, with a few simple mathematical calculations, will figure out which words are more likely to appear not only close to each other, but in sequence. So the word thunderstorm is less likely to appear close to cat than dog is, for example. And we feed it into the algorithm, and it'll churn out, let's say, a number. And depending on the problem, let's say in the case of this problem, we want that number to represent a notion of similarity, right? We want these ideas to be close together, and we want their closeness to be represented by the distance between them. Makes sense so far? Cool. And how we do that and how we conduct training, like I said earlier, as sort of canonical to machine learning, is the idea that it recognizes patterns, and based on some scoring function or based on some feedback, we tell it, yeah, that was a pretty good prediction, and give that particular data point a higher score, move those two words closer together, or say, no, that was a pretty bad one, in which case we weigh that data point less, we move those points farther apart. Now, it sounds pretty abstract, and it doesn't seem like it would come up with anything as meaningful or very helpful in terms of translating from one language to the other. But what a lot of machine learning researchers have found is that by sort of incrementing and letting these machine learning models train for a while and sort of just stacking these simple calculations on top of one another, you find some pretty interesting relationships. So this is a plot of a few word embeddings, just like the ones we have for cat and moon, that were learned by a deep learning model after feeding hundreds and thousands and millions of sentences into it, and by imbuing notions of closeness and farness in terms of conceptual similarity. And as you can see through the dotted lines, even though I didn't tell this computer, this machine, this algorithm that gender existed, that sex existed, that there were gender definitions of certain occupations, it learned that that was significant. For example, the approximate distance between brother and sister is equal to the approximate distance of man and woman. Even though the machine doesn't understand it like I do, it has somehow learned what the notion of gender and sex is. And it's not limited to this particular relationship. The learnings are not limited to this particular relationship. It's not depicted here, but there's also a vector, a list of numbers, for the word crown. And if I added, literally, just the 3 numbers for crown and the 3 numbers for man, I would end up pretty close to the word king. And that's pretty awesome, right? But I didn't tell this machine learning algorithm anything about how to understand language, and just by looking at millions of sentences, it found these relationships. So this process, by which we feed a lot of, at first, seemingly random numbers to the machine as representations of human understandable concepts, turn them into computer understandable concepts, and then shift the numbers around such that the representation in a computer understandable space is related to my human understandable space, is called the notion of training. Now, it doesn't only happen in translation, and it doesn't only happen with words. It can be applied to a lot of other domains as well. A lot of the success of Google Translate and these natural language processing techniques is in that the problem is fairly well defined. This technique of creating a list of numbers that represents words has proven quite useful. It's useful in figuring out movie recommendations. It's useful in creating annotations for Creative Commons pictures, for photos on Wikipedia, for photos on Flickr. In fact, a lot of captions for photos in news outlets are actually now machine generated. But we can also apply it to other problems, such as that of image recognition. So this is a deeper network. It starts over here, close to my hand, and it ends over there on the opposite end of the screen. And unlike words, pictures do have an immediate numerical representation, at least when they're digital photos, right? We have our RGB colors, range from 0 to 255 for red, green, and blue. And as you can see, each layer of the network learns a more general level of the pattern. Let's say for the first layer, it learns that there are lines, edges, straight lines, straight edges. And as we zoom out of the photo, and as we add layers into the network, it understands more abstract concepts. Abstract meaning the idea of a curve over a line, the idea of a shadow, the idea of an outline, and eventually the idea of a car. A lot of how these models are trained is actually through the use of a combination of both machine tools and human tools. So how we measure how good a prediction or an inference or a model is related to the idea of ground truth label. In the case of images, there's this one very large image data set that's been used by a lot of researchers and been used by a lot of companies called ImageNet. And how they were able to create ground truth labels for all of these images such that a machine could learn from them was to use Mechanical Turk. Mechanical Turk is a service, it used to be called Amazon Mechanical Turk. I'm not entirely sure if they're still under the company, but it used to be a service where you could pay very small amounts of money to crowdsource people to label images for you. So if I wanted to teach a computer that this image depicted a car, I would feed millions of images of cars to it, all labeled by human beings with the word car. So then, I guess the notion of ground truth label becomes important, right? Because for simple images of car, we can be pretty confident that 1,000 people are all going to agree that yes, this is a car. For a picture of a cat, yes, we're probably all likely going to agree that whether a cat is on its 4 legs or sitting down or licking its paw, all of those things depict a cat. But what happens when you move into more complex images? This is from another study. It's a little bit difficult to see what's in the photos, but each of the rectangles depicts a constituent part of the photo that the machine is able to identify, and then the machine predicts a sentence that it supposedly thinks describes the photo. In order to check whether the predictions are right or wrong, the researchers compare the computer-generated results with the human-generated labels written by Mechanical Turk. Now, going back to the idea of AI being hard to see and it being more ubiquitous and these techniques sort of defining more aspects of our lives, I'd really like for us to concentrate on this idea that people we don't know, somewhere around the world, granted a lot of them, are labeling photos about concepts that we're claiming are representative of all of our ideas about that concept. A lot of machine learning algorithms work based on historical data. You have a training set, and you have a test set. You train based on your images of cars and cats. You train based on sentences on the internet and on Wikipedia. You predict, and then you check your predictions with a ground truth label. One of the reasons I think it's important to be careful about when we get into more complex problems is because it's harder to define what a correct answer is, right? We can call a translation good or bad if it's a simple, if we're translating something that might not be as politically charged as something else. But once we enter into realms that have more human-related problems into them, more human-related bias into them, we enter into a very gray area. And what I mean by that is, for example, so if we look at some of the notations or the captions given by the machine, they're fairly simple. A small baby wearing sunglasses sits on an adult's lap. And it probably knows that because it's seen a lot of photos of babies, it's seen a lot of photos of laps, it's seen a lot of photos of the act of sitting or the gesture of sitting, and it's seen a lot of things that look similar to this image. But it's still all dependent on what that one Mechanical Turk person said, or those thousands of Mechanical Turk people said about what's actually depicted in the image. So what if a machine learning algorithm had access to a data set of pictures of lots of people, but every time a woman was depicted next to a man, the caption was, "Woman with her boss"? What then would it say when it saw this photo? Now, that might sound like an extreme example. It might sound unrealistic. Like, there are no image data sets where whenever a woman is standing next to a man, the caption is only woman standing next to her boss. But I'll leave that up to the judgment of the audience. I think neither of them is each other's boss. They're both my boss. So, but this goes back then to the idea that it's hard to see, it's hard to tell who's making these decisions about whether or not a data set is representative, whether or not these models are being trained intentionally, accurately, and in a way that I, as a consumer of the products based on these models, agree with. Right? There's a great article by Kathy O'Neill that talks about this problem in a very concrete realm, HR and hiring. A lot of HR groups, whether contracted or as teams in a company, will use personality tests to screen out applicants. And we know that humans are biased. We know that when I apply to a company and I make a bad first impression to the person in that HR team, I'm not likely to get hired, even though in the technical interview I did quite a good job. So we would hope that these machine learning algorithms imbue some sort of objectivity with the numbers. But that's not actually the case. And it is harder to see because a lot of companies do claim the agnosticism of technology. A lot of companies and groups do claim that these numbers are, by and large, completely objective. And I disagree. I think they can be more objective if applied intentionally, but they're not completely objective. Algorithms are used in recidivism programs in the United States. So a judge will use a private company's algorithm to help them decide whether or not someone who has a misdemeanor or has had a prior conviction is likely to commit a crime again. And in that case, when we enter into a public realm, it becomes a little bit more important. The decision becomes a little bit more weighty, right, about what we consider salient features and whether or not we're okay with not knowing what these algorithms are using to decide whether or not I'm going to jail for a crime I haven't yet committed. In hiring programs, these personality tests are able to say with confidence, according to their creators, that this person isn't a good personality match for our company, based on the fact that they're under the age of 25, or based off the 5 questions in our questionnaire that said they might be not aggressive enough, based on the history of our very aggressive candidates, to be a member of this company. But when we confuse the output of an algorithm that we can't test the outcome of with a ground truth label, are we making good assumptions? Is that a good prediction? If I say that I don't want to hire this person because I think that they have a likelihood of having problems interacting with people at my company, or they have a high likelihood of becoming severely depressed in the next year, which if a human said that they would not hire someone for that purpose might get sued. If a machine said that, because a lot of the time these predictions are being made by algorithms from other private companies, it would be called objective. And there's no way for me to check down the line, maybe there is, but I'm not likely to do so as a hiring manager, to check whether or not that person actually did very well in the company that they ended up at. So it's when we confuse the notion of a ground truth label and just the pure output that this algorithm produces that we get into a lot of deep trouble. So one thing out of the other outcomes that I'd like you to take out of this talk is this. It's a quote by Kathy O'Neill, who actually also wrote the previous article. Models are opinions embedded in mathematics. And if we return to one of the first questions that I asked in this talk, how do we make a computer-readable representation of a human concept? We assume that these 3 numbers, whatever they mean to us, are enough to represent this concept. We assume that these 3 numbers are enough to represent me as a human being. You can make any problem into a machine learning problem. You can make anything into a mathematical model. It doesn't mean it's going to be good. It may come out with very accurate predictions, but what about its false positive rate? What about its false negative rate? What happens if the false negatives disproportionately affect a small group of people? What if they affect an already disenfranchised group of people because of the historical data that we decided to use to train the models. So this is not to say that I'm pessimistic about data science and what these machine learning algorithms can do. I'm actually very excited about it. It's part of the reason I'm doing it myself. But I do think it's important to bear this in mind, that every human bias that I have gets encoded in every single line of code that I write. And every single piece of bias that I have and use to create my own data sets for my own purposes also gets encoded then into the models that we analyze and make predictions out of that. So here's one thing I'd like for you to take away about models. There's another thing I'd like you to take away about the data. A commonly used expression in the field is garbage in, garbage out. If you feed bad data into the model, you're probably not going to get a good result. And what I mean by that is, going back to the notion of bias, if I feed in information that, if I as a human being knew sort of every step of the way how the machine was making a decision, and I disagreed with some of those decisions, fortunately we can't do that, I should not expect for it to come out with a prediction that I agree with, because I can't really see that all the time, because a lot of the time it is considered a black box. And a lot of the time, every single decision-making process is not available to me as a consumer. It's hard for me to tell that the prediction is actually garbage. And so I think the onus is on the people collecting the data and on people using the data to make sure that they understand what the biases might have been in collection. If it came out of, let's say, an electronic health record, whether nurses encoded it with computers, whether they wrote something down, scanned the PDFs, and then subsequently hired a third-party contractor to then put it on a database, and then resold it to another company to look at your electronic health record. Each of those steps introduces noise, right? And for all of the noise I believe to be present in my data, if I correct it, if I choose to correct it using statistical methods, that also introduces noise. And we as consumers aren't aware of all of the steps that are taken and all of the sort of assumptions that are being made, however simple or however complex, about the phones that we use, the photos that we take, and the things that we upload on a daily basis. Every time you upload a photo onto Facebook, it looks at your face. It tells its models what do different faces look like, and how can we make our prediction about what they look like better. Thankfully, Facebook has a pretty representative group of people using its product and uploading photos, but that's not always the case. A lot of machine learning models perform better over time with more and more data. A very small number of companies are collecting more and more data about us. And in the ways that I've described, are either using it to construct models themselves or giving it to third-party persons, either through open source for further research, or to use in a consumer context. And so I think it is important that we know that there are assumptions being made about us every day, and that because of where these companies are based and where they hire people from, and the reach of their products in populations that are not of the same representation as the people making them, it's important to recognize that they are opinions encoded in data, and that we also have a way to influence those opinions that are being made about us. So, I know that's a lot of information, and hopefully I didn't delve too much or too little into the technical details. But I'd like to end on the note that even though things are getting harder to see, we do have choices as consumers about sort of what we're willing to talk about, what we're willing to be concerned about, and what we're willing to accept as a purely objective model.